All right, so for this problem, we have two ice skaters, two hockey players. The first hockey player, I'm going to call skater number 1, is standing here. So his initial velocity, so I'm going to put V1 initial, 1 for skater 1, the 0 for initial. So V1 initial is 0 meter per second. So he's just standing there on the ice, and along comes skater 2. So skater 2 is moving with a velocity of 12 meters per second. So I'm just going to label that V2, 12 meter per second. Now they tell us in the problem that skater number 2 has a uniform speed. This is telling us something very important. What is another name for uniform speed? And it actually, more often than not, it would be called a constant velocity. Here they say uniform speed, but in other problems, the more common way to say it is constant velocity. So what is this telling us? Uniform speed or constant velocity? There's another way of saying that. Acceleration is 0. If something is moving with a constant speed or a constant velocity, you know, think of the definition of acceleration. What's the definition of acceleration? Change of velocity over time. So if your velocity is constant, if there's no change in velocity, that goes to 0, which means your acceleration is 0. That make sense? All right, so for guy number 2, I'm going to put I'm going to put acceleration 2 is, oh wait, no. Yeah, acceleration 2 is 0. He has no acceleration. He's just cruising along. All right, now what about skater number 1? So what happens is skater number 2 passes skater number 1. Skater number 1 stands there for how long? 3 seconds, and then what does he do? He starts to chase after skater number 2. So I'm going to draw a line right here. So this line represents the start of the problem. The problem begins the moment that skater 2 passes skater number 1. Skater number 1 stands there for 3 seconds, and then he starts to, does he just move? Or does he accelerate? He starts to accelerate, which is kind of unrealistic. If you've ever ice skated, can you like just, you know, start to accelerate and keep going faster, 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 faster? Is that pretty realistic on ice skates? No, but it's a physics problem. So skater number 1 is going to accelerate until when? He catches skater 2. So the problem ends over here. So here's skater number 2. The moment that skater 1 catches skater 2, that's when the problem ends. So it's kind of like start point, end point, right? So skater number 1, he's going faster, 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 until he catches up to the opponent, right? Now, what's the acceleration that skater 1 has? Skater 1, he moves with an acceleration of 4 meter per second squared. Okay. Now, oh boy, that ceiling is really leaking. Okay, so up here I wrote that there's 2 insights for this problem. There's 2 things that you got to realize. Make some. So the first thing that you have to realize has to do with time. Is the time of travel the same for both skaters? So let's label the times T1 and T2. So this is going to be T1 for skater 1. This is going to be T2 for skater 2. Are the times equal to each other? And by time we mean time of travel. Are they equal or not equal? They're not equal. Which skater is in motion for a longer period of time? Skater 2, right? Because what is skater number 1 doing for the first 3 seconds? standing there. He's not moving. For the first 3 seconds, skater 1 is standing there. 1, 1,000, 2, 1,000, 3, 1,000. During that 3-second period, is skater number 2 moving? Yeah, he's moving. So we need to put this into into equation form. So what can we say about T2? T2, the time of motion for skater 2 is going to be equal to the time of motion for skater 1 plus 3 seconds. So I'll put the unit there, plus 3 seconds. Okay, now what can we say about T1? T1 is going to be equal to T2 minus 3 seconds. And notice that these two equations right here are the same thing. They're algebraically the same thing. Okay, so that's the first insight. The first insight is that we have to deal with time. You know, time 1, time 2, they're not equal. What is the second insight into this problem that you must have? If you don't have this insight, you're not going to solve the problem. It has to do with the distance or the displacement. Well, here distance and displacement are the same because there's no change of direction. What is true about the distance or displacement of both skaters? So the problem begins here the moment that skater 2 passes skater 1, and the problem ends here when skater 1 catches skater 2. What is true about the displacement for each skater? They go the same distance. They're equal. So in other words, we can say, you know, x1 equals x2. Right? The displacements are the same. Okay? So now what we do is so the second insight is that displacement 1 equals displacement 2. Both skaters have the same displacement. All right? So now let's write some equations that we can use to solve the problem. So for skater 1, skater number 1, let's say this. x1 equals 1/2 acceleration 1 t1 squared plus v1 initial t. That's the first kinematic. And by the way, the first kinematic is the most commonly used of the 4 motion equations. I don't know why, it seems to solve the most problems. So when in doubt, try that kinematic first. Okay? Now, skater number 2. I'm going to write the same equation. x2 equals 1/2 acceleration 2 t2 squared plus v2 initial t. Oh, and I should have said t1. That's t1, that's t2. So guys, you got to specify, like, you know, which t are you talking about? Which a are you talking about? Notice my subscripts here. a1, a2, t1, t2. All right, so for skater 1, something in here goes to 0. What goes to 0 in this equation for skater 1? The initial velocity. So this part of the equation goes to 0. And we're left with this. We're left with that. Which part of the equation? Oh, dude. Sorry. We got drippage here. You know, I just maybe moved to a lab table. Yeah. Okay, for skater number 2, which part of the equation goes to 0? Looking at this equation, the acceleration. The acceleration goes to 0. And what we're left with is displacement 2 equals v2 times t2. And v2 is a constant, right? That's the velocity of skater number 2. All right. What do we do to these two equations now? What do the two skaters have in common? The displacements are the same. Okay, so let me shrink this down. I need a little more room. Oops. Oops. What's going on here? Huh. I think I'm on the wrong layer. There we go. Okay, so what we're going to do, are you guys with me on this? So we're going to substitute the two equations together. So what we get is 1/2 a1 t1 squared equal to v2 t2. So now we got to deal with the times. So here we have t1 and t2. So what I'm going to do is I'm going to take t2, I'm going to take this equation for t2 and plug it in over here. So now we have 1/2 a1 t1 squared equals v2 t1 plus 3. So then we got to distribute the v2, so it becomes some algebra. So again, we got 1/2 a1 t1 squared equals v2 t1 plus 3v2. Okay, so at this point, let's plug numbers in. I'd say let's go ahead and plug the numbers in. So what is a1? a1 is 4. And you know what? You could leave units off here. The units are all in agreement. I think it'd be easier to leave the units out. Not every physics teacher would agree with that, but you know, I say it's okay. v2 is 12. So what we're going to get here is a quadratic. When you simplify this down, you're going to get 2t1 squared minus 12t1 minus 36 equals 0. Okay, kind of a bummer. You know, quadratics are never my favorite thing. But if on your calculator, how many of you have the quadratic, you know, where you punch in A equals, B equals, C equals? That's kind of a cool thing to have because it's not totally uncommon to get quadratics, and it'll just speed up your solution. Okay, so this is going to give us two answers for T1. So T1 is either going to be positive 8.2, or T1, because quadratics are going to give you two solutions, or it's going to be negative 2.2. Which answer is not the correct one? The negative one. Time is not going to be negative. So this is not the answer. The time of travel for skater number 1 is 8.2 seconds. And that's what they're asking for in part A. How long does it take skater 1 to catch skater 2? It takes 8.2 seconds. Okay? All right, part B, how far has skater 1 traveled in that time? So this is just going to be, this can be solved with a motion equation. So let's use, so for part B, we now have the time. So let's use x equals 1/2 at squared plus v initial t. And we're going to do this for skater 2. We're going to do this for, no, I'm sorry, for skater 1. So this is x1, a1, v1. Okay, skater 1 has no initial velocity. That goes to 0. So x1 is going to be 1/2 4 meter per second squared times 8.2 seconds squared. And this comes out to be, I believe, about 134 meters. Somewhere in there. All right. Yo.
Can we also add 3 seconds to 8.2 and then multiply it by 12? Because since he's going out.
Yeah. In fact, that'd be what you could have done is you could have found how far skater 1 went because the displacements are the same. You could have solved for x2, which would be v2 times t2. So that'd be 12 meter per second. And then the time would be 11.2. And that will give the same thing.